Welcome back to the next video, everybody. Today's video is on the Etale fundamental group. So I would see Milne's Etale cohomology, MEC, SGA1, and lectures on Introduction to Grothendieck's theory of the fundamental group for more details regarding the following discussion. Now, we're not going to get too into the Etale fundamental group here, but we're going to give a little bit of the basics. So let's let FET over S denote the category of finite Etale S schemes. And we'll be assuming throughout for ease that S is non-empty and connected. And we'll let alpha be a geometric point of S. That notion was defined last video. So the fundamental group pi, which can also be written pi sub 1 of S alpha, of S at alpha. This is defined to be the group of automorphisms of the functor that sends y to y of alpha from FET over S to sets. So y of alpha was defined last time. This is all of the points in y mapping to alpha. And this is akin to the theory of covering spaces, the group of deck transformations in the ordinary topological fundamental group from like an algebraic topology class. Okay, so what are its elements? To be clear, an element sigma of pi is just a collection of permutations sigma sub y of the sets y of alpha, and then one for each y in FET over S. Such that for every morphism y to y prime in this category, the induced map from y of alpha to y prime of alpha better commute with the sigma sub y. So you should have commuting squares in each of those cases. This makes pi a profinite group, and as we might recall from a previous video long ago in my series of talks on Fermat's last theorem, that makes it a compact Hausdorff topological group, in which the open subgroups, which in this case happen to be those containing the kernel of the map that sends pi to the permutations on y of alpha for some y, form a fundamental system of neighborhoods of 1. So this is all kind of familiar generic theory of topological profinite groups. Okay, the only detail there that you actually have to check is that these are the open subgroups. All right, let's let F pi denote the category of finite sets X that have a continuous pi action on them. Then y of alpha is an object in this category by construction, right? And so Grothendieck's theorem from the previous video, or maybe it was 2 videos ago now, can be restated to say that the functor that sends y to y of alpha from FET over S to F pi is an equivalence of categories, actually. And this functor commutes with products and disjoint sums you can check pretty easily. And so expressing y as a disjoint union of its connected components then must be the same thing, or corresponds rather, under this equivalence of categories, to expressing y of alpha as a union of its orbits under the action of pi. Okay, so unions of connected components on one side correspond to unions of pi orbits on the other side. That's pretty neat. It'll get neater though. The fundamental group pi1 S alpha can be thought of as a functor on geometrically pointed connected Noetherian schemes S alpha. So a geometrically pointed Noetherian scheme would just be one that has a distinguished point that's geometric. We'll call the point alpha. And so this is to say that a morphism F from T to S of such schemes, so these geometrically pointed schemes, this should induce then by functoriality a homomorphism F lower star from pi1 T beta to pi1 S F of beta in a natural way. And this should happen so that the base change functor that sends y to its T base change from FET S to FET T corresponds under the equivalence of categories from the previous slide to the process of viewing a pi1 S F of beta set as a pi1 T beta set via the homomorphism F. Course. Okay, so this is all sort of standard stuff akin to what happens in ordinary algebraic topology, essentially. The other thing to realize is that pi1 of S alpha is determined up to inner automorphism by S. And so if alpha prime is another geometric point of S, the functors that send y to y of alpha and y to y of alpha prime are just isomorphic. And so what is this akin to in algebraic topology? This is akin to the notion of a homotopy class of paths from alpha to alpha prime, of course, right? And this induces an isomorphism rather, from pi1 of S alpha to pi1 of S alpha prime. Nothing surprising, really, if you know your algebraic topology. Okay, if K equals kappa of S, so the residue field at S, and alpha is given by the embedding alpha tilde from K into omega, the usual stuff we talked about with geometric points last video, then the group of K automorphisms of omega acts on the left on omega, of course. And so then by equivalence of categories, it should act on the right on spec omega. And so for each y in FET over S, it should act on the left then on y of alpha, because that's just the S scheme homomorphisms from spec omega to y. So another way of saying this is that we have a homomorphism from K automorphisms of omega to pi1 of S alpha factoring through the quotient, the Galois group of K sub S over K of K omega. And what's K sub S here? It's the separable closure of K and omega. And so another way of saying this yet like a fourth or fifth way now, is that we have a natural homomorphism from the Galois group of K sub S over K to the fundamental group, right? And you can explicitly show then that if S is like a singleton S which you could also think of as spec K if you like. This homomorphism is actually an isomorphism. And the equivalence of categories above that we said held in general, we can actually explicitly check holds in this specific case. And then also in this specific case, I mean, you might ask, what's the reverse categorical equivalence? You send X to spec of pi maps from X to KS, where X is a finite set equipped with a continuous pi, which pi in this case will be the Galois group of KS over K action. And what's this pi maps from X to KS? That's just the set of K algebra maps from X to KS that commute with pi. So there you go. In case you wanted to know the equivalence of categories going the other way, there you go. So this is nice. Okay. So geometric points sort of correspond to this nice homomorphism here from a Galois group into the fundamental group. So what's the upshot of this whole discussion? I think this is a really good summarizing point here. If alpha is a geometric point of a Noetherian scheme S, the functor that sends G to G of alpha is an equivalence of categories between the category of finite Etale group schemes over S and the category of finite groups equipped with a fundamental group action. So that's a nice way of thinking about finite Etale group schemes. All right, and so next time we'll begin looking at the connected Etale exact sequence. So I'll see you then, and thanks for watching.